All right, everybody, this is our last unit of the year. We're going to go over intermolecular forces and properties of solids and liquids. This first lesson is to introduce you to terminology related to intermolecular forces and how they work. So first, let's go over states of matter. This is mostly a review. You have some characteristics here of gases, liquids, and solids, as well as particle diagrams. Make sure you can draw particle diagrams for solids, liquids, and gases if asked. I also have a chart on Schoology that gives you a list of characteristics in terms of arrangements of particles and volumes and shapes. Solid and liquid state particles are closer together. We call those condensed states. So if you see something about condensed states, that's what it's talking about, just solids or liquids. The phase of matter that something exists in is based on two characteristics that are actually in opposition to one another. The kinetic energy of the particles as well as the strength of attraction. So particles are moving, which is going to move against the tendency for them to stick together. So depending on how those two characteristics come into play, that will tell you if something is a solid, a liquid, or a gas. This chart is the one that I have linked on Schoology as a separate document. And you can see a lot of the vocabulary here, stuff that was talked about in Regents Chem and kind of assumed. Something to keep in mind with phase changes is that when things change phase from solid to liquid to gas, the molecules themselves remain intact. You're changing the forces between the molecules, not the ones within the molecules. So anything that's a force within the molecule we would refer to just as a bond, intramolecular. It's within. So that's where you're just dealing with what we just covered, ionic, covalent, and metallic. Intermolecular forces, like this on our little friend here, are what's responsible for little reptiles like this to be able to stick to walls. So in terms of the magnitudes of forces or the strengths of these attractions, the types of bonding vary in strength, and also types of intermolecular forces vary in strength. So covalent bond is obviously a bond. It's an intra. And then once you, but those are much stronger. If you look at the values here, they are much stronger overall than any of the types of intermolecular forces. So ionics, typically the lattice energies are even stronger than covalent bonds. So if you had to rank attractive forces, ionic would be strongest, then covalent, and then you enter the realm of intermolecular forces, where hydrogen bonding is the strongest. But you can see it's much weaker than a covalent, then followed by dipole interactions and London dispersion forces. So just a diagram here to show you how intermolecular force works. So if we have a molecule, the bond that holds the hydrogen to the chlorine is a covalent bond, right? They're sharing the electrons. This here would be the intermolecular force that would allow one HCl molecule to stick to another HCl molecule, and it's much weaker and more temporary. They are strong enough to control physical properties, though, like boiling and melting points. So the stronger this is, the higher the melting or boiling point would be, which also affects things like vapor pressure and viscosity, which is the ability of something to flow. So think syrup versus water. As a whole, intermolecular forces are classified as what are called van der Waals forces. Something I don't like in Regents chemistry is that Regents chemistry calls dispersion forces van der Waals forces, and they're not. Van der Waals force is not a particular type of intermolecular force. It kind of encompasses all of them. So the types of intermolecular forces we're going to be looking at here are London dispersion forces, ion-dipole interactions, which is basically how an ionic compound would dissolve in water, dipole-dipole interactions, and then hydrogen bonding. And they're listed here basically in order of strength. So the first type, which is the weakest, is a London dispersion force named after this guy, RIP. So a London dispersion force is a temporary intermolecular force that are what attracts nonpolar molecules to other nonpolar molecules. So a nonpolar molecule is something that does not have a net dipole. So something like methane, right? Symmetrical distribution of charge. Carbon dioxide, right? Things like that. So these don't have an overall positive side or negative side to them because the polarity of the bonds are symmetrically arranged, and they are they kind of cancel each other out. So there's no net dipole here. But it is possible to make something like dry ice, which is solid carbon dioxide. So some sort of a force of attraction is possible that would hold this nonpolar molecule to another nonpolar molecule. And that's what's called dispersion force. So different terms that you might see here: London forces, dispersion forces, or dispersion interaction forces. Typically, I'll be abbreviating these LDF. I'm fine with you abbreviating them LDF, and I think everybody else would be okay with that too as far as grading goes. As long as like write it out first and then abbreviate it from there on out. So dispersion forces occur in all molecules. So if you're given a molecule and you have to identify all types of intermolecular forces, LDFs are always in there. And then you can go look at the characteristics of the molecules and see, okay, was there something else at play here? Is it a dipole? Does it have hydrogen bonding as well? This is a dispersion force, though, is really an induced dipole. So it's kind of when one molecule, the electrons shift temporarily, creating a polar molecule, and then that polarity induces polarity on its neighbor. So this is kind of a diagram that would show that. So if you had something like even a noble gas, right? Noble gas, complete valence, PEL, electrons are always moving. So if the electrons shifted to one side of this atom, it would leave a more positive side on this, side of the atom, and a more negative side on the opposite. So if it's near another atom of the same type, it will induce polarity on its neighbor, because this positive side of this atom will attract electrons from its neighboring one as well. So they could create a temporary dispersion force. Now it's weak because it will shift. When the electrons shift, it falls apart. The same thing can happen if I had two molecules. So if I had two hydrogen molecules near each other, and the electrons of this hydrogen molecule shifted and became more concentrated on this side, leaving kind of like a naked proton over here, because hydrogen only has one electron of its own anyway, and another hydrogen molecule is nearby, it will induce a dipole by pulling those electrons to this side of the hydrogen molecule, creating that dispersion force. And again, it's weak because as soon as the electrons shift, it's back to falling apart. This just is kind of repetitive. Skip, just explain that. You can read it yourself. You can read that yourself too. It's a skip. All right, now this word they loves on the AP. So the tendency or the likelihood of this happening varies depending on what substance you're talking about. So the tendency of an electron cloud to be able to distort in this kind of way is called polarizability, the ability of it to become polar. So there's a trend that you're going to need to memorize here. The size and shape of the molecule will impact its polarizability and also the strength of its dispersion forces. A long, skinny molecule, like a linear, let's say hydrocarbon, would tend to have stronger dispersion forces than an isomer of it. So this would be like another version of the same molecule. So this one would have stronger intermolecular forces because it has a greater surface area to it. So long, skinny molecules tend to have stronger intermolecular forces because they can align on top of each other and have more places for interactions to occur. Whereas when they're bunched up like this as an isomer, there's only so many points of contact you can have. The size of the molecule also plays a factor. So it's not just let's say the length of the chain or the shape of the molecule if you're talking about isomers, but also the size of them. So these are all halogens, and we're going down the group, and they become heavier as you go down, right? Atomic masses are increasing, and look what happens to the boiling points. Likewise, we have the same thing happening with noble gases. And it's not because they're heavier per se, but it's because the larger the atoms are that are involved, they will also have larger electron clouds. And the larger electron clouds have greater polarizability. So that's a real good explanation that you could give if you were asked to explain a trend in boiling points in a particular set of atoms or molecules that fall into a particular group. This graph shows you a same kind of trend, but it's dealing with hydrocarbons. So if you go back to organic chemistry, we have a bunch of alkanes here that we're just increasing by the number of carbons. And you can see how the boiling points increase as the molecular weight increases. So again, it's not the weight, but it's actually the polarizability of the electron cloud. So if you were given a graph like this on a multiple choice, a free response, and you were asked to explain the trend in boiling point, you could say the strength of dispersion forces increases due to the larger electron clouds, which have greater polarizability. Additionally, if you were given like a set of C5H12s, but they were all different isomers of each other, different shapes, the linear version of it would have the stronger dispersion forces because it has more surface area to the molecule to have more contact points with a neighboring molecule of the same type. Next, we're going to look at attractive forces between polar molecules. So you're looking at dipoles. Dipole attractive forces of any type are stronger than any type of dispersion force, but they're still weaker than regular chemical bonds like ionic, metallic, and covalent. An ion-dipole interaction is basically what happens when you dissolve a soluble ionic compound into a polar solvent such as water. So we talked about solubility, but when an ionic compound dissolves, the ions dissociate. Why do they dissociate? Because the attractive force of the polar solvent towards the ion of an opposite charge is stronger than the force of attraction, or it's able to be interrupted when you dissolve it. So if we had, this would be an ionic compound like sodium chloride. We have a 1-to-1 ratio here. Oh, actually we don't, but you know. And these would be my water molecules. So the hydrogen ends of the water molecule would pull off the anions. The oxygen ends of the water molecules would pull off the cations. I mentioned this with bonding already, but if you have to indicate a dipole moment, you would do that with an arrow, that the arrowhead would point towards the negative portion of the molecule, which would have the higher electronegativity, a greater pole, and the positive end of the tail of the arrow, you'd put a plus sign through, and that would be the positive end of the molecule. So there. So if you had water molecule, that's how you would indicate the dipole. This is what we did in Regents Chem, this like kind of sigma positive or sigma negative to indicate, and you could also do it with arrows. When you have a molecule that is nonpolar, like carbon dioxide, I don't like that it doesn't have a double bond here, but if you have a nonpolar molecule like this, there is polarity in this bond and polarity in this bond, but because of the geometry, right, the electron regions maximize the space between them at 180 degrees here, the polarity of this bond, it perfectly cancels out the polarity of that bond, so there's no net dipole on it. So this would be a nonpolar molecule, and it would only have LDF. Dipole interactions are when you do have polar molecules near each other, the positives and the negatives attract one another and form these intermolecular forces. So a permanently polar molecule will attract another permanently polar molecule through a dipole interaction. Here are some polar molecules. Actually, no, this one's nonpolar. But there's several polar molecules here. Dimethyl ether, methyl chloride, which is chloromethane. This is ethanol, and acetonitrile. You don't have to remember that from Regents or anything. But they have similar molecular weights, relatively speaking, but their polarities are different, so their boiling points are different. The more polar the molecule, the higher its boiling point. You will not have to deal with any sort of calculations involving dipole moment. These are graphs that have several polar molecules on them and shows the trends in their boiling points. So if you look at the blue line, we have hydrides that involve, so hydrogen based compounds that have group 14 elements in it. And then we have this green line, which are hydrogen compounds that have group 15. This is group 17, this is group 16. So you see, like, here we have this weird anomaly in terms of a graphic trend. Instead of just a gradual incline like we do with that blue line, we have this starting out really high for the red, yellow, and green, then it dips down and starts to increase again with the boiling points. So these three molecules must have something going on that the other molecules in their trend group do not. So the molecules that are following the blue line are nonpolar molecules, and they follow the trend of increasing mass. So you think like CH4, SiH4, GeH4, they're all going to be the same. Like, I'm drawing this cross because they're tetrahedral shapes. Here, this red line does follow the trend for H2S, H2SE, and H2TE, which sulfur, these are all the same, oxygen, sulfur, selenium, and tellurium are all in the same group, but you see this anomaly, which is water. So the anomaly can be explained by what is hydrogen bonding. So the first graph that had all the lines on it, I circled H2O, NH3, HF. Those were the three that were the anomalies in their groups as you looked at those graphs, right? It started up high and then dropped and went up again. Those three molecules have extremely polar bonds and are polar in shape and form what are called hydrogen bonds between them. A hydrogen bond occurs when you have a molecule containing hydrogen that is directly bonded to either a nitrogen or an oxygen or a fluorine. These bonds are extremely polar because nitrogen, oxygen, and fluorine have very high electronegativities as compared to the hydrogen. So the polarity of this bond is really in favor of the oxygen. The electrons highly either nitrogen, oxygen, or fluorine. The electrons highly favor attraction towards them. What happens then, if you think about electron clouds here, is that those electrons are so towards the other element involved, they basically leave the nucleus of the hydrogen exposed because hydrogen only has one electron in its cloud. So it's basically just a proton and one electron. So if that electron is spending most of its time towards the nitrogen side of the molecule, what am I leaving exposed? I'm kind of leaving this strong positive charge exposed. So the polarity of the bond is extremely polar. So those are the three elements that would have to be bonded to hydrogen in a molecule in order to form hydrogen bonds with its neighbor. This basically explains what I just said. So the three that you would need to know right off the bat that do hydrogen bonding are water, ammonia, and hydrogen fluoride. There are others, a lot of alcohols, because you would be given the structure of an alcohol. But here, this bond is very polar, okay? So this right here would allow for hydrogen bonding to take place with a neighboring molecule. It's that portion. DNA and RNA would work the same way. Hydrogen bonds are what holds the two sides of a DNA molecule together. Let's see, that's just talked about it. Just talked about it here. Hydrogen nucleus exposed. Here's more hydrogen bonding in water. Here's more hydrogen bonding between ammonia. So it doesn't have to be the same molecule, but here this nitrogen portion is very partially negative. We have another situation here with the water, very polar bond, partially positive. So you can have a hydrogen bond there as well. Here's what happens with DNA. So why can thymine only pair with adenine in DNA? It's because of the molecular structure. There's two possible places where hydrogen bonds can take place. This is carbon. Yeah, that's it. Whereas with cytosine and guanine, we have three possible locations for hydrogen bonds to occur. This is that same graph again. This summary chart is on Schoology that goes through the different types of intermolecular forces. And then here's an example. Which molecule is capable of forming stronger intermolecular forces? You have to go to the structure. Structure dictates properties and functions.
because they know he's not near 90. So am I going to get
Okay,
back?
so nonpolar molecule, LDF is the only intermolecular force. Polar molecule, oh, okay, so it's a dipole. Is it a special dipole? Yes, because of the superpolarity of this bond on each side, this has LDF because everything does, and it also has hydrogen bonding. So that's super fast intro to intermolecular forces. The other video I posted will be helpful as well.